Yeah? Start talking?
Yes, please.
Okay, so, well, it's a pleasure to speak here at StanCon, and I guess Bayesianism is said to be a form of religion, and so I guess it's appropriate that we're in the chapel. And I guess we should have a note of humility, or just a sense of how unimportant everything we do is in the grand scheme of things. And I don't just mean like war and peace, it's happening without us. I guess, the last time that MCMC really made a difference in the world was when our namesake Ulam used to design the H-bomb. So I guess, we can thank Stan Ulam for a few decades of peace, followed by ultimate annihilation. But like just for example, can you hear me still?
Yes.
Yes? So like here I am in the East Coast speaking to you, and through the miracle of Google Hangouts, and I don't think there's any Bayesian statistics being used in any way, right? And this is just an amazing technological feat that we can have this phone conversation here, and not only was Stan not used, but like no Bayesian program, they didn't use bugs to do this, or even write their own variational code or whatever. They just didn't need Bayesian inference. And similarly, the airplanes that got you over to California didn't use any Bayesian inference that I know of. And I guess some of the drugs that we take have used some Bayesian inference, a little bit. Like we've done some work in drug development, but I think most of them probably don't. Now, I do feel there's room for improvement. So I guess I do feel that if drug companies use Bayesian decision-making more formally, and the drug approval process were more Bayesian, I guess I do think we'd be better off. Like, I do feel that lives would be saved. So I do feel there's the potential for Bayesian inference to make a difference in our life, but I think it's important, just since we're concluding the conference, just to emphasize like how unimportant we all are, how minor we are, how minor all our work is compared to people who are doing amazing technical feats, or people who are saving lives, or anything like that. And I guess one of the directions where we'd like to move would be to reform science and policy analysis. So even like somehow there are policy decisions that get made, and maybe it would be good if Bayesian methods were used. It seems to me the problem is that we use that policymakers have this desire, and not just policymakers, but drug approvers, like the people who do all sorts of policy, have the desire to make decisions based on certainty. And so there's this idea that science creates these hard nuggets of certainty. Like you could imagine science as being like some very hot furnace where we pour in like coal and it crushes it into a sharp, shiny diamond, right? Through the efforts of science. And our data becomes sparkling diamonds of truth. And from there, policy analysts can go to the what works clearinghouse to decide what methods to use for education policy, or drugs can be approved, and so forth. But somehow it turns out science isn't really like that. And my colleagues and I have argued that whether or not science was ever like that in the past, it's not going to be like that now, that we really need a model for science that's closer to quality control. So the goal of science is not to prove things that are statistically significant or have Bayes factors that are more than 20 or whatever. The goal, somehow, science is this ongoing process where we're supposed to be gradually improving. And the funny thing is, I guess we live that because that's software development. So that's what we all do. So I like to feel that there's like a ladder of things that we do in life. Like, we'd like to be on vacation, but we work. And then, like, people who do science don't want to do any statistics, but they they have to become statistics experts in order to do science. It's really annoying. Statisticians have to become experts in statistical computing. I hate statistical computing, but I do it all the time because I need it to solve my statistical problems. And people who do statistical computing have to really become software designers, and programmers, which isn't really what they bought into. And of course, software designers have to design hardware, and they have to be involved sometimes in the hardware, which is, of course, not where they want to be, and so forth and so on. Chemists have to become physicists. All the way down the line. And so really as software designers, we're very aware that when we design software, we think in terms of quality improvement, we don't think in terms of statistics. I mean, classical statistics, we don't say like, what's the posterior probability that our software has no more bugs? Because it doesn't really matter. Or do we want to prove that this software is better than the previous software? And that's sort of a meaningless thing. I mean, I guess maybe you have to do it to do a NIPS paper or whatever, but that's not really what we're after, right? We're trying to like solve problems one at a time, and so it's just, I guess mostly I want to kind of make you. I just want to reflect a little bit about how maybe the statistics that we're doing could be a little bit closer to the reality that we want to model. And one reality is that two pieces of reality that are very accessible to all of us. One is software development, and the other is education, because we've all been students, whether or not we've been teachers. And I think in both of those cases, we're aware of this continuous process. Or you can think of a replication crisis in science done along those lines. So I think the big picture for statistics is first to recognize that we should not be too proud of ourselves. We haven't done that much. What have we done? Like opinion polls, some stuff in drug development. I guess there's some genetics, statistical genetics. There are some problems that statistics has made a big difference on. But most of technology doesn't use a lot of statistics. To the extent that we can do better, I think it's by having our models be a little bit closer to what we're trying to study. Now today, Daniel said that things went a little late, so he said I could talk until 5:35, so I could have one more minute, and then it will be time to stop. I guess I can go. Can I go for a couple more minutes?
Yeah.
Okay. So I wanted to talk about some problems that I wanted to solve in STEM and what we need to do about it. And I think people who have chatted with me or have, read some of the STEM discourse will be familiar with some of these things, but it's mostly hierarchical linear and logistic regression with big data. But big data is not so big. So for example, we did a survey. I was involved in a survey with a few 100,000 respondents, which was from a large organization. It was a survey about sexual harassment, and they had data from many locations and a lot of individual characteristics of the locations and some of the people involved and the survey respondents. And they wanted to identify where problems are better, where problems are worse, and adjust for things. It was kind of an open-ended exploratory problem of the sort that we see a lot of with large surveys. There were some specific questions they wanted to know about prevalence. So you want to do a little bit of multi-level regression and post-stratification, but you all want to learn what's happening locally. And so it's sort of a natural fit for a hierarchical linear and logistic regression. But it was kind of tough because of all the data. It runs really slow. And I don't mind a computer program that takes a few hours to run if I know what I'm going to do. It's like, if someone gives me a recipe to make some delicious dish, and the recipe is 38 steps, and it takes me 5 hours, and when it's done, I'm gonna have this amazing cake, then I'll put it in work. But what I really don't want to do is have someone give me this scrawled thing that says, here's my best guess of the recipe, but you're probably gonna have to try a few dozen other things before it works. And by the way, everything you try is gonna take 5 estimates of the variance components, and then hard coding that as priors and other things. And I'd like to just be able to fit it in STAN. A similar problem came up with our analysis of something we did with the National Board of Medical Examiners. We were looking at doctors, the rate at which doctors have disciplinary actions. And it turns out that doctors who scored lower on the medical boards are more likely to have disciplinary actions later. But when you do that kind of thing, you want to control for a bunch of things like how old is the doctor, how long has he or she been practicing, what state they live in, because getting a disciplinary action can vary by state, what's their specialty. There might be some specialties that involve more disciplinary actions than others. Then also the relationship with the exam score seems to be nonlinear, that if your exam score is really low, like just barely passing, you have a higher chance of getting a disciplinary action, but then when it's moderate or high, the relationship seems weaker. And so again, I'd like to just fit a model with all these factors, but it was difficult because of the size of the data. We're working with a company looking at bank transactions, just millions of transactions. There was another company that was doing analysis for a store, and they had sales of every item in every store, of every product line, and every day for a few years. And again, like, we found ourselves doing a lot of, just like doing a lot of stuff by hand, like saying, well, first we're going to take averages and subsets and different things, and then try to put it all together again. So why is this hard? It's hard because for two reasons. I mean, you have a lot of data and you have a lot of parameters, so each step takes a long time. And we don't always understand these models so well, so sometimes there are problems with the geometry of the model. We run across the Folk theorem of statistical computing sometimes, and so for various reasons, these things take longer than we would like. What are the solutions? I'll get to the solutions in a second, but first I want to answer two questions. First is, why do we want to use Bayesian methods at all in these problems? And second, why do we want to use STAN? Because, I mean, it's not like, okay, STAN's our thing, and so we want to use STAN, but I have particular reasons for doing that. So why Bayes? So first, we often have prior information, so we want to be able to incorporate that. I think the traditional way we incorporate prior information in statistics is we fit our models, and then if the results seem to make no sense, we kind of jiggle the models around until they give a reasonable answer. That's like a crude version of Bayes. We'd rather do better than that. Second, regularization. So especially when the number of groups are small, you fit a multi-level model, the group level variance estimate can be very noisy. This is something it took me a while to realize the importance of this problem. Because for the longest time, like my usual mode of operation, which might be yours, is I get some data and I fit a model, and then I look at the results and I make some conclusions and I go on to a new problem. Every once in a while, though, I've been in a situation which is more of a production line. Like, for example, my colleagues Jeff and Justin, the twins at Columbia, were fitting MRP in a bunch of different surveys and a bunch of different survey questions. And they had kind of a production line, and I got to see a lot of the estimates as they were running off the production line. And I noticed how noisy the estimated variance components were. And I noticed that you'll have very similar problems, and one data set, the estimated variance component is essentially infinity, and so it's doing no pooling at all. And then the next one, it's zero, it's doing complete pooling. In any given case, it's like, oh, zero, it's doing complete pooling, fine, there's not much variation, or conversely, the variance is so large it does essentially no pooling, well, that's fine, that's life, it seems to make sense. But when you look at the production line, you realize how noisy these estimates are, and how much of what we take seriously in our inferences is really being jerked around by noise, and that means unregularized inferences. So that's another reason why we use Bayesian methods and not just use some off-the-shelf classical hierarchical regression model. The next thing is that with multi-level models, they work better when you have group-level predictors. Because when you have good group level predictors, then the residual group level variance is small, so you do more partial pooling, you get better estimates. But group level, when you have group level predictors, you'll have less data to estimate them, and priors are going to be more important. So you have to kind of bite the bullet and put the priors in. Finally, why Bayes posterior uncertainty? So you have, a lot of these are business examples, and you want to feed the outcome into a business decision. Or in polling, so a big application of Bayesian inference of Mr. B. I have surveys, I want to adjust, I want to take my survey, I want to break it down and adjust it by age, sex, education, party ID, political ideology, urban, rural, suburban, married, unmarried, kids, no kids, religion, education, income, et cetera, lots of factors. I want to post-stratify. And I want to get not just a point estimate, but an uncertainty. So as we learned in the 2016 election, the polls were pretty good, but some of the state polls, people weren't adjusting for enough, and their uncertainties were too low, and that led people to be overconfident. So Bayesian is really a natural way to handle that problem. Not that it's perfect, but it means it's trying. Okay, why SCAN? So why SCAN? Because whatever off-the-shelf software we have to fit these models doesn't do everything I want. So some multi-level modeling software won't handle non-nested groupings. Other multi-level modeling software can handle non-nested groupings, but it doesn't allow you to put prior information on the group level variances. So things blow up, get too noisy if you have a small number of groups, or prior information on their coefficients. There are also things such as partial membership, like you have data on kids within schools, and you have a kid who switched from one school to another. Well, you can hack that, right? But you don't want to be hacking everything. What about non-parametric models? As I talked about in the example of the doctors, I would like a non-linear, non-parametric model of how things vary by their medical board scores. Measurement error models. So in SCAN, as you know, you can just put in a measurement error model, just one more line in the code. It's other programs aren't going to allow you to do that. And just more generally, modularity, because it's all, everything is supposed to snap together. Now, what are the solutions? Because our programs are too slow. So these are a lot of things that we're working on, and I guess I wanted to, I sort of since I had the opportunity to give the closing talk, I wanted to get you all worked up about solving the problems that I want to solve. Right? That's what it's all about. That SCAN's all about solving my applied statistics problems, and you're all here to help me. That's so what are we doing? Well, we're hard coding some of the auto diffs. So I guess recently there was some work on setting up recoding linear and logistic regression, and now it's, I think, 3 to 10 times faster, just by cutting out the middleman and setting up the entire regression model. I think something similar maybe could be done with multi-level models. We're working on parallel computation in different ways. There's algorithms like ADVI. Now, ADVI, of course, doesn't always work. But we would like to have it be a bit more stable. GMO, gradient-based marginal optimization. We're also putting in INLA, integrated nested Laplace approximations. So all of these have there's a common theme, which is the choice we make between approximate computation of the model we want to fit or exact computation of a different model. And we get into big arguments at the SCAN meetings about this. So, I want to fit this model, and I don't know how to do it fast enough. So if I can get an approximation, like a mode-based approximation or an integrated mode-based approximation, such as in GMO or INLA, then maybe I can correct the approximation, maybe the approximation is fine, or else maybe I shouldn't do that. Maybe I should just fit a simpler model. We've been talking about the network of models, and that's the idea that we never fit just one model, so let's be more open about that. Finally, I remain excited about EP, about expectation propagation and data splitting algorithms. So one thing that I find, let me just step back for a minute and say that the genesis of STAN was that when we were writing Bayesian data analysis and wanted to give demonstration code for Metropolis algorithm and Gibbs sampler and all that, we had some examples, and I tried to write some code that was as generic as possible. And then I started to realize that every time I'd write my own Metropolis algorithm or Gibbs sampler, most of the code was kind of the same. I was copying the code, and it struck me that if I could, I was making my code more and more stylized, until at some point it seemed like it should be possible to write a computer program to do it for me. Well, then, of course, STAN is different because we use HMC, and it's much more complicated. But I found that in applications, there are certain things with big data that we always end up doing. We end up splitting the data, fitting the model to separate data sets, using inferences from simpler models as priors, taking hyperparameters and setting them at fixed values and then relaxing them. So here's a little tip, by the way. I think it's better to set the hyperparameter at a fixed value and relax it than it is to start with it having a flat prior and then go closer, because the flat prior is unregularized. Well, currently there are some issues. So one is the syntax of STAN. It's actually kind of hard. Like if I want to say I think theta is very close to 0.42, and I want to start by saying it's exactly 0.42, well, if you want to say it's data rather than a parameter, you have to change the program. If I want to say, well, I'm going to give it a prior with mean 0.42 and standard deviation 0.01, normal 0.42, SD 0.01, very sharp, I can't put that in STAN straight. If I put that in STAN, it's not going to work because it's in the wrong scale. I need to scale it. I need to introduce another parameter. So I have to take theta and scale it by a factor of 0.42 and get it to do that. So a lot of the things that I would like to do that are very natural in model building and STAN in our development aren't so easy to do. We need to make our syntax a little bit richer. We need to actually be able to say, like a parameter can actually have a prior associated with it that's sort of more of a native thing. Like now, there's no such thing as a prior in STAN. There's no such thing as a prior, there's no such thing as a likelihood. All there is, there's just an objective function. There's a target, and you just add stuff to the target function. And it just happens that priors add things to the target function, likelihood add stuff to the target. But there's no such thing as a prior associated with a parameter, which is very general, which is kind of cool, but for a lot of our model building, we actually would like to have that. It comes up in a lot of applications. Now, there has to be a way, we would put this in STAN, but not in a way that constricts the language, right? Not in a way that stops us from having our freedom. But currently, we have to do, STAN is almost too general. So that's one thing. Another thing is data splitting. And so we wrote the paper on EP as a way of life, but that's a paper. It's not in there in STAN. There's not an R program either. Like if you want to do it, you have to figure out how to do it and go through the steps. And that's kind of fine, because if it was an automatic algorithm, I think it would be really slow at this point. But I think that a lot of what we do in statistical computing, there's this development where you start with like individual problems and tricks, and you do them over and over, and they become methods, and at some point they become programs. And I feel like STAN is the culmination of a lot of that. I mean, look at all the people who no longer have to waste their time, writing Gibbs samplers and all that. But still, for big data problems, we are still sort of doing a lot of the data splitting and a lot of the kind of hacking by hand. And I think we want to work at formalizing that. So we're really working in three strands in that sense. That one strand is just making computation more efficient through a brute force. And the second strand are approximate algorithms that use mathematical reasoning to, like algorithms like in-large GMO or ADBI, they use math ideas to get us closer in our approximations. And then the third thing is, I think, ultimately formalizing in various ways in the syntax ideas for for the use of big data. I mean, I just find it embarrassing when I'm talking to someone I'm consulting, I say, oh, well, try dividing your data into 10 pieces. Like, I tell everybody that. Why can't the program do it automatically? So we're kind of working on that. So I want to conclude by thanking you all for coming to StanCon. And also, I really, more than anything, I want to thank the Stan developers. I used to say I've never written a line of C++ code in my life, but then I found out Stan's in C++, which means that every time I write a Stan program, I'm writing C++ code. But that's like all of it. You know, I'm only a user. I haven't written any lines of Stan. I've only supplied some algorithms on occasion, and so I'm very grateful. I'm grateful for like the U.S. government and so many of our funders for supporting this work, which is all open source. And I'm so grateful for my colleagues. And of course, we all get paid, but still, like developing stuff that's so useful for so many people, including me. So I think maybe we can all thank the people who wrote Stan.
Do you want to take a few questions, Andrew?
Oh, yeah, sure.
I have a question. How fast is fast enough? When will you be satisfied that this model will extract out? Okay. So if the model runs for 5 hours now, when will you be happy?
The question is, if the model runs for 5 hours now, when will I be happy? Well, I said be happy in 5 hours, but then the trouble is then I probably want to change the model, and that'll take another 5 hours, so I don't know when I'll be happy. It'll take many groups of 5 hours before I'll be happy. 5 hours wouldn't be enough. I think that's the problem. Oh, but you mean, I think you mean like, okay, if it ran in 2 seconds, I'd be happy.
Right.
But I guess, you know, there must be some intermediate. I'd be 5 times as happy if it ran in 1 hour. And I'm really happy that it runs in parallel. So it runs 4 times as fast on my laptop just because of that. So I feel like every bit helps. It's hard to draw the line because it is kind of qualitative, right? Like there's like a threshold below which, like, if it takes too long, people just won't do it. Or like for any given client, right? There's a threshold for which, like, okay, they're not going to do it. And if it goes faster than that, they'll actually start fitting models in Stan. But it depends on the context, because as you know, we've had clients who at first have been wary of Stan, but eventually say, we got to bite the bullet. And I do feel that, like, generality and accuracy are more important than speed. I mean, I do think that we'd rather have algorithms that give the right answer and take a long time, because then we can make them faster. I mean, that seems like generally the right way of going. But then at some point, we have to make them faster.
Anybody else? Well, I think we got it. All right. Yeah, I'm walking over.
Thank you for the talk. This has been great. So my background is not statistics, and I recently been using Stan, and I'm just absolutely stunned by the capabilities for what it can use in industries that don't traditionally use it, like medicine, pharmacy, and stuff. There's obviously a pretty significant gap in terms of like engineers versus statisticians, and I think this is doing a good job to close it. But what do you see that look like over the next like 5 years? Like how do these models become more and more integral in industries that don't traditionally use them?
You don't have to repeat that.
Oh, okay. Yeah, I mean, I guess it depends on the industry. I mean, I think that So at just a technical level, a lot of the stuff in AutoDiff got developed in the optimization literature in engineering before being used by statisticians. I guess it's often is that like, it's typically like people can't solve a certain problem that they want to solve. I don't know, I mean, I would say my quick answer would be like, case studies. I don't know how to like communicate. Like if there's, I guess maybe someone needs to write a book on like engineering models and standards and like, because there are those, there's that guy who wrote the street fighting math book, that guy who teaches at MIT or taught at MIT, and Sanjoy, something or another. And it was all like, it's like physics, engineering kind of models. And I think people like, those are would be very natural for STAN. So like somehow it would be a great subject for a book or something. I mean, I don't know how to reach people, but like there's presumably a juicy class of problems like that are not big data problems. Like they're kind of small enough that STAN could fit them in seconds or minutes or whatever. And I do remember when I was a physics student, like there was a lot of curve fitting you do. I'm sure it's all different now, but like you'd have data on the multi-channel analyzer and fill the Lorentzian, and you'd spend lots of time doing stuff which is essentially statistics. Like you'd want to fit least squares, but there was a trend, an underlying noise trend, and you'd have to subtract. And I think, these things would be so much easier. The way like physicists and engineers do data analysis, it's like, I think they tend not to want to make a generative model. So they start with the data, say, here's the data, I want to pick out this curve, I need to correct for this, I need to correct for this, I need to correct for this. They're jumping to the solution. And the statistical idea is very exciting, which is that you forget about the solution, you try to actually just model the process, and then look at your answer and get closer and closer. So I think a few examples of that, like written up in that way, could be very powerful. I mean, I would do it, but like, there's so many other things I need to do, but it does seem like a good idea. You could do it.
All right.
There's a question over there.
Thanks, Andrew. We'll do more. Do you guys want to do more questions? Yeah. It's 3 o'clock, when they're done. Right. All right. Yep. One more.
I am a big fan of yours. I preach your gospel to all my coworkers. So my question is kind of more about what you were just talking about on engineers and the machine learning types working with the data first instead of trying to build those models. How else do you think we can get those people more into our style of modeling, and do we want that?
Well, I think, the machine learning is a little different. I think machine learning has a lot of generative models, and so they're much more statistical. I mean, there's a couple directions to this. So I think one direction is with the machine learning is, can we, and this stuff we've talked with Dave Bly about also, is can we basically kind of bootstrap, as it were, machine learning methods and kind of make them more Bayesian. So like, there are simple things like you have a machine learning method that makes predictions. Well, you have 4 processors in your computer, so run it 4 times in parallel and you get 4 estimates, right? And then that gives you a crude posterior uncertainty. So like people don't always even think, like things like that. And then and then there are things related, like take a machine learning method and treat it as a generative model, and then try to get some aspect of the posterior. So like methods like ADDI are kind of an attempt at that. Then another approach is to post-process, is to say, well, you have some engineering style method, whatever it is, and it gives you predictions. Now instead of just taking these predictions and running with them, let's think of them statistically. So let's do post-stratification. So people, machine learning don't always use to do post stratification. You get predictions. You can get predictions for everyone in the population. You can post stratify. Let's get uncertainty estimates. Let's go back and use our cross validation to get uncertainties, and then there are ideas that try to integrate statistical thinking more deeply in. I think it's. If there's a lot of people out there just solving problems I would have no idea how to solve. So if someone's doing something like these, like curve fitting, and I think they could do better with a, generative model, maybe they should just start from scratch and fit it in Stan or whatever. On the other hand, if someone has some program that's already recognizing cats on the internet, I can't use Stan to recognize cats on the internet. Then it's more like I'd say, well, what's our comparative advantage, right? Like, let's go try to feed this into a decision analysis or whatever. Let's not try to talk people out of doing stuff that works.
Any other questions? Let's thank Andrew.